Okay, before we get going into SAT math lessons and topics, we want to get on the same page. Make sure we have a set of fundamental skills. These are skills that, well, they might even go back to elementary school. They're core things you need to know how to do because you're going to use them over and over again on SAT math topics. So you really need to just do a checkup and make sure we're good, we're on the same page with them to go. So the skills we're going to cover on fundamental math skills today are multivariable calculus, matrix algebra. Oh, come on. These aren't fundamental skills. That's not right. That's not what we're covering today at all. All right, how about 2 plus 2 equals 4? Oh, come on. You guys are messing with me now. That's just ridiculous. Okay, these are not the skills we'll be covering today. Well, we can do some addition, but if we're going to do addition, let's start with at least addition of fractions. So how do we add, subtract, multiply, divide fractions, all that good stuff? Let's take a quick look. If I add fractions, it's probably a review for everyone, but 1/2 plus 1/3, for example, the first thing we do is find a common denominator. So the common denominator between 2 and 3 would be 6. The product of the two denominators is always a common denominator. Maybe not the least common denominator, but always a common denominator. Okay, so I don't just add 1 and 1. What do? I need to convert this to an equivalent fraction, each one, 1/2 and 1/3, over 6. That means I'm multiplying the denominator by 3 on the first fraction. Well, I don't want to change the value of that fraction, so I need to multiply by 3 on the top as well. And for the 1/3, I multiply that denominator by 2 to make it 6. And again, I want to multiply by 1 without changing the 1/3 value, so I can do that cleverly by multiplying by 2 over 2. Now I have my adjusted numerators. It's 3 times 1, 3, plus 2 times 1 is 2. The answer is 5/6. Okay, that's well and good. Everybody kind of knows how to do that. But what if I have variables? Are you comfortable adding and subtracting fractions with variables? Suppose I had the following. 1 divided by x plus 1 plus 1 divided by x minus 1. Well, how would we do that? We'd find a common denominator, which is the product of the two denominators, which is x plus 1 times x minus 1. Oh, and guess what? I know that's a difference of two squares. That becomes, if we multiply it out, x squared minus 1. That's a little more advanced. We'll get into that in our SAT math studies, but we'll just keep that in mind. So the next line, I'm going to write that as x squared minus 1 in the denominator. Now, I can't just do 1 plus 1. A lot of students try to do that with variables. Why, I don't know, because we didn't do it with the numbers out top. We know we had to take a second step of finding the equivalent fractions. So how do I find the equivalent fractions here? Well, again, I know I multiply the x plus 1 times x minus 1 in the denominator here, which means I'm going to multiply by x minus 1 in the numerator too. And I'm going to do the same kind of process, same thing I did above conceptually, multiply by x plus 1 over x plus 1 on the right times the 1 over x minus 1. And I can multiply out the numerators. X minus 1 times 1 is x minus 1, plus 1 times x plus 1 is plus x plus 1. Okay, my 1 negative 1 cancel. I'll end up with 2x over x squared minus 1. And that's how we add or subtract fractions of variables. So you definitely want to get comfortable doing that. Let's see another example of this at play. What if I had 3 fractions? 1 over a plus 2 over b plus 3 over c. This might be a little more complicated. How do we do this with 3 fractions? Well, okay, first step, common denominator. Always a product of the 3 denominators in this case. So a times b times c, ABC. Now again, I don't want to just add 1, 2, and 3. I'm going to actually give you a tip. We can do what we did up here, but it works out to the same thing as this. I can take my numerator and to adjust each numerator to its equivalent fraction over the ABC denominator, I can take the numerator and multiply it by each of the other denominators. So that'll be 1 times BC. The next numerator, I'll also multiply that by the other denominators. That's 2 times AC. And the third numerator, I'm going to multiply that, well, same idea, by the other denominators, not its own denominator. That's 3 times AB plus 3AB. I'm essentially doing what I did up above, but when I have multiple fractions, knowing this little trick or process is much faster and more effective. And that is the answer. So now we know how to add, subtract fractions of variables. Okay, this might be digging back a little deep, but how do we divide fractions? If I divide 2/5 by, say, 1/3, remember our keep, change, flip. I hate that acronym. Didn't use it back then when I learned math. I just say dividing by fraction is the same as multiplying by the reciprocal. But if you guys like your keep, change, flip, you can keep it. Essentially what we do, we take 2/5. If we're dividing by a fraction, we keep 2/5, we change division to multiplication. I'll use the dot notation for multiplication. And we flip the fraction 1/3 to 3/1, and we multiply. Multiplication's easy. It's just 2 times 3, multiply out the numerator, 6. 5 times 1, multiply out the denominator. Your answer is 6/5, okay? So be careful. Sometimes we see that in vertical form. So what if I had 2/5? And let's suppose it was divided by 3 with a larger horizontal fraction bar. That essentially means everything above the fraction bars are in parentheses. So this is actually different from above. This is 2/5 divided by 3, which is the same as 2/5 times the flip or reciprocal of 3, 1/3, which is 2/15. We can almost think of it as 2 divided by 5 times 3, and that's the answer for that. And bear with me, I'm going to race through some of these topics. Again, our goal here is just to refresh your memory on some of these, and if you need more work, you can research it a little further on your own. So let's talk about some basic rules that we learned, well, probably back in elementary school. Things like order of operations, PEMDAS. And how about our beloved associative, commutative, and distributive properties? Yeah, they were fun, let me tell you. Had great laughs back in school on those. PEMDAS, order of ops, basically says do everything left to right unless you run into the following priorities. Parentheses, do parentheses first, then exponents second, then multiplication, division at the same level. So it's division first, like 3 divided by 6 multiplied by 2. I wouldn't do the multiplication first, 6 times 2. I do 3 divided by 6, which is 1/2, and then I'd write out the rest, and then I'd do 1/2 times 2, which equals 1. Okay? Addition, subtraction, that works at the same level as well, just like multiplication, division. Now, there's all kinds of controversy. You might have read about this. If you grew up in England, you might have learned BODMAS or other methods. They all boil down to the same thing. It's just a rule to make sure we work the same way. So let's look at a quick problem. Okay, if I had the following, 10 times 4 minus 2, quantity 4 squared divided by 4, divided by 2 divided by 1/2 plus 9. Whoa, okay, where do we begin? Well, we're going to begin going left to right. Oh, I do see parentheses, so I'm going to start there. 4 squared divided by 4. Well, that just becomes 4. So now I have 10 times 4 minus 2 times my 4 in parentheses, divided by 2, divided by 1/2, plus 9. Okay, what next? Do I have any exponents? No, I took care of those already, so I don't have to worry about that. How about multiplication, division? I'm going to work left to right on my multiplication divisions first. That's here, that's here, that's here. Okay, so let's put those together on the right a little bit. 10 times 4 is 40, minus 2 times 4 is 8, divided by 2, I'm going to write these step by step because I've got a 3-part series here of division. Okay, and I want to be careful. So that's 40 minus 8 divided by 2 is 40 minus 4 divided by 1/2 plus 9. Again, I'm working left to right within division here. So 40 minus 4 divided by 1/2 is essentially 4 divided times 2, right? Our keep change flip. So that's 8. 40 minus 8 plus 9. Now my multiplication division is gone. I just add, subtract left to right. 40 minus 8 is 32. Plus 9 is 41. Is that my right answer for this whole thing? Yes, fortunately it is. I had to hold my breath there. That was long enough and scary enough that who knows, maybe it wasn't, even though I should know the rules, right? Now, I know it's going to be hard for you to believe, but after dealing with these in elementary school, coming back to them at a later date, they're actually pretty cool if you think about them. They really help us do a lot of what we need to do. The associative property, it works for addition and multiplication for certain. It occasionally might work for division and subtraction, but usually not, right? But always addition and multiplication. So what does that say? That really says how I associate, in other words, where I put my parentheses and things together, doesn't matter. The answer is always going to be the same whether I'm adding or subtracting. So 2 plus 3 plus 5 should equal 2 plus 3 plus 5. And sure enough, it do. 3 plus 5, according to our PEMDAS, is 8. 2 plus 8 equals 2 plus 3 is 5, according to my PEMDAS in parentheses, plus 5. They all equal 10. Same holds true for multiplication. Commutative property. What is commute? I forget that a lot. Well, if I commute, I'm moving, I'm changing from my house to my workplace. It's the change. If I change the order or the positioning, the commutative property tells me in addition and multiplication again, it always does not make a difference to the answer. You can do that. So for example, 2 times 3 equals 3 times 2. They're both equal to 6. So for multiplication, does not matter to the answer. Okay, that's good. That helps us a lot because sometimes we multiply things out and we get AB plus BA, and we have to realize those are the same thing. That's AB plus AB, really, so it's 2AB. I can put together the like terms. How about our distributive property? Whoa, this becomes a source of mistakes, so be careful, watch your signs. Essentially, it says A times B plus C equals, I multiply the outside term into the parenthesis terms, A times B, plus my A times C, and I've just simplified or distributed, okay? However, note, 2 things. One, students don't think about going in the reverse direction, called factoring. The reverse of distributing is pulling out, say, common factors or factoring. Not binomial factors of quadratics, which is actually an analogous idea, but factoring common factors in this case. A very useful skill you want to get comfortable with on the exam. Underutilized. Okay. Point number 2. Distributive property leads to a lot of plus and minus sign errors, which is a huge problem on the exam. You cannot afford to make positive, negative sign errors on the exam. So be careful if you have something like 2 times x minus 3 minus x minus 4. How would I distribute this one? What's the equivalent of this? Well, it's 2 times x, 2x. 2 times minus 3 is minus 6. Okay, so far so good. Minus times the x is minus x. And here's where students mess up. If I have a negative in front of the parentheses and or a negative inside the parentheses, be careful of either situation. Negative, this is really -1. There's no coefficient written there, but it is -1. -1 times -4 makes +4. 2 negatives make a positive. And then I can combine like terms. 2x minus x is x. Minus 6 plus 4 is minus 2. Make sure you're careful about your signs when you distribute. And if you thought I was going fast before, I'm really going to race through our number types. So our number types include real numbers. What's a real number? Well, it's basically anything you can put on a number line. 0, pi, -5, 1/2. These are all real numbers. If it could be on a number line, it's a real number. What can't be on a number line? I, our imaginary number. We define that as the square root of -1. Why? Because if I square a negative number on the number line, it becomes non-negative, 0 or positive. I square positive, becomes positive. So anytime I square a real number, I cannot get a negative. But I squared is square root of -1 times square root of -1, which equals, sorry, that looks like a J, but it's an I. It equals -1. An imaginary number can square to give me a negative real number. Real numbers can't. So we define this as our imaginary number. What else isn't real? Well, infinity. Aside from the concept of where would I put it on the number line, at the end, beyond the end, it's not even a number, so don't even start, right? It's just a concept. So these are the exceptions to real numbers. And by the way, when we put together, say, real numbers like a plus or minus b, assume these are constants that represent real numbers, times I, we call this complex numbers. Why is it complex? I don't know. It's probably complicated. It has real numbers and imaginary numbers, so we call it complex numbers. Why not? Okay? Whole numbers. Whole numbers are, well, it's just 0, 1, 2, 3, and all your counting numbers, including 0. So don't forget, 0 is included in the whole numbers. I don't know what a rational number is, but I do know what a rational number is. A rational number can be expressed as a fraction of integers or whole numbers. Well, wait a second. We didn't discuss integers yet. What's an integer? Well, integers are just whole numbers plus the negatives. So -1, -2, -3, etc., going down, plus our whole numbers, 0, 1, 2, 3, and onward. Okay? So if I have a fraction of integers, a over b, that is a rational number. Okay? In decimal form, what would that be? Well, 1 over 4, that would be a finite decimal. That's a rational number. 1 over 3, well, that's an infinite decimal, but at least it's infinitely repeating, 0.33333, and we denote that by the horizontal bar over the 3. What's not a rational number? An irrational, crazy number. That would be something like pi, 3.14159, etc., etc., etc. It just keeps going, and it never repeats. That's the key. If it's a non-repeating infinite decimal, it's irrational. So more common is any square root, square root of 2, square root of 3, square root of 5, square root of 6. Anything that's not a perfect square as a square root is an irrational number. And yet, it is a little crazy. For those of you who don't know the story, Pythagoras, you probably know the Pythagorean theorem, a squared plus b squared equals c squared for right triangles. Do you know a student proved that you could have irrational solutions to his theorem? Which really isn't his theorem, by the way. And you know what he did to the student? He took the student out. He was so mad at him, that was considered such bad form, he took him out on a rowboat into a lake, and he drowned him. Yeah, that's a true story, believe it or not. So, moral of the story, be nice to your teachers. Okay, other number types, even numbers. Well, even numbers only apply to integers. The concept of even does not even make sense for fractions or decimals, so don't even think of it outside of integers. But an even number is anything that's divisible by 2 or a multiple of 2, okay? So we might ask questions like, is 0 even? And there might be some debate there, but 0 times 2 is 0, so 0 is technically a multiple of 0, multiple of 2, so therefore 0 is even, I would say, yes. Okay? But again, any number that's divisible by 2 or has 2 as a factor is even. It ends in 0, 2, 4, 6, or 8. All right, yeah, we know that. And then every other integer, 1, 2, 3, 1, 3, 5, 7, 9, will be an odd integer, okay? What about primes? What's a prime number? Well, again, prime only makes sense in the topic of integers, right? So they must be integers. Is 1 a prime number? If we say a prime number is a number that's divisible by only 1 in itself. Well, you'd think that might fit the definition, but the definition of prime actually excludes 1. It excludes 0 too. 0 and 1 are neither prime, nor you might know the word composite. Composite is a number that's divisible by more than 1 in itself, and of course they have to be greater than 1. So our first and only even prime number is 2. It's the only even prime, and it's our lowest prime. All other primes are odd. 3, 5, 7, 11, and I can go on and on and on. By the way, you should get to know your primes pretty well up to 50. Recognize things like the largest 2-digit prime is 97, largest 3-digit prime is 997. This familiarity with the numbers will help you, maybe, on the exam. Okay, so that's my quick wrap-up of number types. Let's move on. Let's talk squares and square roots. If I had a number like 3 squared, the 2 in the upper right corner, the superscript 2, is what we call the exponent, or the square. The 3 below it is what we call the base. So the base 3 to the 2 power, or 3 squared, it means multiply that base 3 times itself 2 times. A lot of students confuse squares with doubling. They say, oh, 3 squared is 6. It's 2 times 3. No, it's not. It's 3 multiplied by itself twice. It's a very different answer. That's 9. Okay. What about the square root? Well, the square root of, say, 9 would be that number, call it n, such that it multiplies it by itself 2 times. Notice it's a second root, but we don't write the square. We don't have to in form, just like we don't write 1x to the 1 power. We usually just call that x. Okay, so that number multiplied by itself 2 times is equal to the value in the radical. So whatever n is, that's the square root of 9. So, well, what is that? That's just 3 times 3, as we saw. That equals 9. So the square root of 9 is 3. Square roots are always the primary root. By definition, they are positive. Okay? So, well, we think we know squares and square roots, but there are a few things we need to know. By the way, do not do the same thing in reverse as squares. Square roots do not have the number. Again, it's that number multiplied by itself that equals the result in the radical. By the way, if I didn't mention, that symbol there, that is what we call your radical. Okay? So, what are some cool features of squares and square roots? They undo each other. For positive values, that means they're inverses, like addition, subtraction, multiplication, division. If I start with 3 and I square it, I get 9, as we just saw. But if I take that 9 and I take the square root of it, I go back to 3, and round and round and round I can go forevermore. One undoes the other. That can be really useful for solving equations. Okay? What else? What else do we know about squares and square roots? Well, a couple things. We know we want to learn how to simplify square roots. How do I do that? Let's say I had the square root of 72. Okay, great. I just solved my Pythagorean theorem. I have the answer. I look among the answer choices. Wait, there's no square root of 72 there. What the heck is going on? Well, they might have simplified the answer. Essentially what we do is we factor the number under the radical to find perfect squares. Well, I know 72 is 8 times 9, for example. And when I use square roots, I can multiply or divide. I can break out the square root of the radical symbols. I can make that square root of 8 times the square root of 9. Do not, please do not do that with addition subtraction, okay? This is not true. The square root of 9 plus 16 does not equal the square root of 9 plus the square root of 16. That's just not true. That's square root of 25, 5, which does not equal 3 plus 4, or 7. So don't try to use this with addition subtraction. Multiplication, division, thumbs up. It's going to work, okay? So square root of 9 is 3, so, okay, this is 3 root 8. Well, can I keep going? Are there any perfect square factors of 8? I think so. Let's try and look at that. So the square root of 8 I could rewrite as the square root of 4 times 2, which I know is the square root of 4 times the square root of 2 separately. I can do that again in multiplication, break apart my radicals. And square root of 4, well, that's 2. So this becomes 3 times our square root of 8, which is 3 times 2 times root 2. The answer is simply 6 root 2. Oh, I see that answer. I didn't see the square root of 72, but 6 root 2 is among the answer choices. That's my answer. And that is how we simplify radicals and how we break apart radicals in multiplication division, not addition subtraction. So there are a few other tips and tricks on square roots you might want to know. If you need to estimate the value of a square root, say what's the square root of 50? Well, what do I know? I know 7 squared equals 49. I know 8 squared equals 64. By the way, it pays to get to know your perfect squares up to, say, at least 20 to 25 squared. Then I can figure out, well, 50 is between 49 and 64. So the square root of the squared, as we said, they undo each other. The square roots would be between 7 and 8. In fact, we're really close. 49 is really close to 50. So it's approximately 7, just over 7 is what the square root of 50 would be. That's a quick way to approximate by knowing your perfect squares and then range bounding it and figuring out what a good estimate of that square root should be. We can also use it the following way. If I know my squares up to, say, 25 squared, I might ask the question, what is the square root of 3.24? Well, I know 18 squared is 324. Okay? By the way, if you're not used to that, one good method is the method that 18 and 18, just 1 times 1 is 100, 8 times 8 is 64, so I've got 100, 64, and then 8 times 1, the crosses is 8, another 160 in total. Add it all together, you get 324. Nice quick way to do any perfect squares if you need to do that. So, if 18 squared is 324, this is really, again, factoring. You got to work your factors. Is 324 times 1 over 100. Well, I can break that out. What's the square root of 324? Times the square root of 1 over 100. That's just 18 for the square root of 324. And for 1 over 100, well, that's just 1/10, right? Nice little trick is anytime I take a square root of something with even numbers of zeros, I just have the number of zeros. So 18 times 1/10 is 1.8. That is the answer. And I could quickly determine that just by looking at square root of 3.24, knowing my perfect squares and factoring. Okay? So gaining a familiarity with the numbers can be really useful on the exam. But hold on, we're not quite done with our square roots. We also need to learn how to rationalize square roots. Well, what the heck does that mean? That means if I have something like 1 over the square root of 2, we do not want to leave the radical in the denominator. So how do I get rid of it? How do I get that radical out of the denominator? Well, I'm going to multiply by that radical over the radical. Radical 2 over radical 2. Square root of 2 over square root of 2, which is, by the way, anything divided by itself is just 1. So I'm multiplying by 1, not changing the value of the expression, but it changes the form. 1 times root 2 is square root of 2. Divided by root 2 times root 2 becomes 2. Again, squaring the square root undoes it. You just end up with a value in the radical. And now I've rationalized my radical. There's no more radical in the denominator. Okay? Well, what if I have something like this? 1 over 1 plus root 2. How do I get rid of the square root there? Can I multiply by square root of 2 over square root of 2 again? I don't think so, because I'm going to end up with a 1 times the square root from the denominator there, which is not something I really want to do. So what else can I do? Well, I'm going to multiply by what we call the conjugate. So if a plus b is the form, a minus b would be its conjugate. So for 1 plus root 2, I'm going to multiply by 1 minus root 2 over 1 minus root 2. What's that going to do in the denominator? Well, again, this is basically our difference of two squares. My root 2 terms will drop out. I'll end up with the square of the first, 1 squared, 1, minus the square of the second. Square root of 2 squared is minus 2. And my numerator, I just need to multiply it out. I'll get 1 minus root 2. And of course, 1 minus 2 is negative 1, so this becomes essentially root 2 minus 1. I kind of did a couple steps in there to get that by knowing 1 minus 2 is the negative and multiplying it through. That's what we do with our denominator if I have a more complicated expression. Okay, and we can extend the idea of squares and square roots to higher orders. So for example, x squared, we said x was our base, 2 is our exponent. Well, why does it just have to be 2? Can't we have 3, 4, x, what we call cubed, x to the 4th, and so on, etc., etc.? I mean, x to the 4th would just mean, following our same rules of squaring, multiply that base together the exponent number of times, that is 4 times. Yeah, we can do that. And what would it mean then to have the 4th root of, say, 16? That would be the number that multiplied together 4 times, not just twice, but 4 times, equals 16. Well, I know what that is. That's 2 times 2 is 4, times 2 is 8, times 2 is 16. So the 4th root of 16 is going to be 2. So yeah, we can learn to do these. We can extend beyond just simple squares and square roots. So there's some rules associated with. One thing we want to know is anytime I raise to an even exponent, well, we saw with real numbers, it always makes the number positive, or non-negative to be more exact. But cube roots and cubes and fifth powers and odd powers, they can be negative. Minus 2 times minus 2 times minus 2 becomes minus 8. Now, I can't have a square root of negative 4. That doesn't work. That's imaginary, right? But I can have a cube root of negative 8. That is, as we just saw, minus 2. That number multiplied by itself 3 times, that gives you the value in the radical, minus 8. So we have a difference between odd roots and even roots. And furthermore, we've got various laws we developed to work with the exponents, regardless of what they are. Not just 2, but 3, 4, etc. Let's look at a couple simple ones. X to the 0. Well, that's a weird one. What does it mean to multiply the base 0 times? Well, guess what? It means it's just 1. Anything to the 0 power, 10 to the 0 power is 1. Okay? Next exponent law. If I multiply bases that are the same with different exponents, I can add the exponents. X cubed times x squared is x to the 3 plus 2, or x to the 5th. Okay? That's called our product rule. Our quotient rule is kind of the same thing, but we're dividing. If I have x cubed divided by x squared, well, that's x to the, now I subtract the exponents. The same base to the subtraction or difference of the exponents. That's x to the 1, or we might just write that as x. Now, our power to a power rule. That's a fun one. X to the 4th raised to the 2nd power. Well, that's essentially, if we think about it again, remember, raising to a 2 power says multiply whatever's in the parentheses twice. That means x to the 4th times x to the 4th. And we saw up above in rule 2, that means I add the exponent, so that's x to the 8th. Well, yeah, I could have gotten there the same way from this rule, my power rule, which simply says multiply the exponents. X to the 4 times 2 is x to the 8th power. And that's my power to a rule. It's how I deal with situations where I see a power to a power. Now we start getting a little more interesting. My expanded power rules. X, y raised to some n power. Well, it's almost like I'm distributing the exponents through multiplication. X to the n, y to the n. And x divided by y to the nth power. Well, again, it's x to the nth divided by y to the nth. That's what allowed us to work with our square roots before. We could say the square root of 9 times 16 equaled the square root of 9 times the square root of 16. By the way, a square root is really a power that's essentially 1/2. In this case, the exponent equals 1/2 for a square root. Okay? And I could do that in division too. The square root of 1/4 is the square root of 1 over the square root of 4, and that's just 1 over 2. Remember, I could not do that with addition subtraction. There is no expanded power rule for addition subtraction. Okay? Negative exponents. What does it mean to have x to the negative n? Well, negative exponents do not make numbers negative. They don't change signs. Remember that. Never ever change signs on a negative exponent. It's always the reciprocal. 1 over x to the n. If exponents are multiplying the bases, then the opposite of that would be essentially taking the reciprocal, dividing the product of the bases. So x to the n is negative 1 over x. So what would that be? Let's say 5 to the negative 2 is 1 over 5 squared, which is 1 over 25. That's how we would use that. And the hardest concept that students get used to, hopefully, is what we call rational exponents. Remember the word rational, like rational numbers? Always translates to fraction. If you hear rational, you think fraction. M divided by n, technically that's the equivalent of radical, the base to the numerator power inside the radical, to the nth root, to the denominator root. Okay? So what would say 8 to the 2/3 power b? That would be the cube root, the denominator root of the base to the numerator power. Well, 8 squared is 64, so this is the cube root of 64, which is essentially what number multiplied by itself 3 times equals 64? Well, that's 4. The answer is going to be 4. 4 times 4 times 4 is 64. And that's probably the fastest wrap-up of the exponent laws you'll run into. It's worth getting to know them by heart. There are problems that will test you on that more complicated situations on the exam. Couple little small tidbits I want to bring up that students sometimes make mistakes on, don't realize. What if I gave you the square root of x squared? Most students think, oh, that's x. Well, not quite, actually. It equals the absolute value of x. Another issue is, what if I have minus 3 squared and minus 3 squared? What do they evaluate to? Minus 3 squared, PEMDAS says do your exponents first. So I get 9, and then I apply the negative. So the answer here is negative 9. If I look at the second case, I do my parentheses before my exponents. So I have to make it minus 3 times minus 3. And the answer here is plus 9. Notice that difference, if it's in parentheses, the negative 3 or not. It's a very different result. By the way, if you're ever plugging in for a formula, always use parentheses. Always plug in around parentheses. So you pretty much always get this case, just in case that confuses you at any point. Okay, one last point I want to cover. I said I'd wrap it up real quick, and we've been at it a little while now. So I just want to discuss expressions and equations. Essentially, you're going to see basically 3 things you would need to do for any given question, more or less, on the exam in general. You'd either need to evaluate, simplify, or solve. Students kind of get confused between these sometimes. Evaluate means essentially plug in a number. Let's say I have f of x equals 3x squared plus 5. What does that mean if I need to evaluate f of 5? That means plug 5 into my expression. That would be 3 times 5 in parentheses. Note when I plug in, I put in parentheses. That's in case if I need to distribute or anything else, I do that properly. Squared plus 5. Well, that's 3 times 25. Note how I'm using my PEMDAS implicitly here as well, which is 75 plus 5. It's 80. I evaluated for a given x what my y value or my function value is in this case. So evaluate problems deal with expressions. Note, not equations. Simplify, I might have something like x squared minus y squared over x plus y. How do I simplify that? Well, at first blush, you might look at it and say, whoa, that's not easy to somehow make simpler unless you know your difference to 2 squares. X squared minus y squared is, or factors into, x plus y times x minus y, the conjugates. And if that's all over x plus y, then guess what? Even though there's some addition and subtraction you need to worry about generally, they're all within the binomial. So essentially have a factor times a factor divided by the same factor, x plus y, x plus y. The binomials are the same, therefore they cancel top to bottom. This whole thing simplifies to just x minus y. All right, again, simplify works with expressions. There's no equation inequalities. I'm not solving anything. Students sometimes confuse that. Solving is when I have an equation, an inequality. I might have, well, let's keep it a very simple two-step equation. 2x plus 5 equals 10. Well, I can pretty much eyeball that and see 2x has to equal 5 or x has to equal 5 halves. But let's solve it. Two steps, subtract 5 on both sides. The 5 minus 5 cancels. 2x equals 10 minus 5 or 5. Now I divide through by the coefficient to isolate my variable x. And sure enough, x equals 5 halves. And that's your answer. So in most problems, just remember in general, they're going to ask you to evaluate, simplify, or solve some type of expression or equation. All right, that's great, because that's leading into my last topic, which I want to discuss, is how do we solve some basic equations? How good are you at doing that? And I'm going to add just a few cases of complexity onto our simple two-step, multi-step example. What if I had some variations to our simple sort of two-step, multi-step case? What if I had parentheses in my equation, or I had variables on both sides, or fractions or denominators in my equation? What if I had squares, square roots, or other functions involved? How do I go about solving these equations? It's just a first step before we get into our more complicated SAT math. How do I solve basic equations? You need to know this. So for example, if I had 2 times x minus 3 equals 10, what do I do? Well, this is pretty simple. If you have parentheses, distribute. 2 times x is 2x. Minus 3 times 2 is minus 3. And that equals 10. Then what do? I combine like terms if there are any. X's, x squareds, y's. They're all separate terms that are unlike and I can't combine. But if I have 5x squared minus 2x squared, I can combine it to 5 minus 2x squared is 3x squared. It's kind of like 5 apples less 3 apples is 2 apples, that kind of idea. So if I'm down to a two-step, I do the same thing as I did before. I add 3 to both sides and I divide by 2. Okay, that's well and good. Parentheses. Generally, we multiply out and simplify. Not always. Sometimes you need to factor or cancel right away. But that's a good rule of thumb. Variables on both sides. What does that look like? Well, what if I had 5x plus 10 equals 7x minus 30? I have variables here. I've got x here, x here. When I solve an equation, I want to isolate my variable on one side. So guess what? I'm going to subtract the 5x off of one side. That's how we usually get rid of the variables on one side. That cancels. I end up with 10 equals 7 minus 5 is 2x minus 30. I'll add 30 to both sides. 2x equals 40. X equals 20. That's how we deal with variables on both sides. Okay? What if I have denominators or fractions? Suppose I have, not fractions I want to add or subtract. We did that already. What if I just had, like, say, x plus 5 over x equals 10. What's the first thing I want to do? The very first thing, assuming I've already combined like terms and simplified as much as I could, I want to get rid of those denominators. They're bad, very, very bad, if you want to think about it. How do I do that? Well, the opposite of dividing, which is what a denominator is multiplying. Multiplied by the entire denominator. Here, my denominator is x, so I'm multiplying both sides by x. If that were more complicated, 3x squared minus 10x plus 5, well, guess what? I'd multiply both sides by 3x squared minus 10x plus 5. I want to get rid of the denominator, the entire denominator. So those cancel. Don't try to distribute. That's not going to help you. You did this so you could cancel out on the left side. X plus 5 equals 10 times x, 10x. Now I'm back to the case of variables on both sides. What do? I subtract the x's from both sides. And that will take me back to the case of a two-step equation. And then what do? I solve a two-step equation. So you can see how we're adding layers of complexity. You want to make sure you know how to undo certain complexities when you see them. What about simple squares or square roots? What about x squared minus 9 equals 7. Well, the first thing I want to do, if I have any function, whether it's square, square root, or could be trig function, absolute value function, whatever it is, I want to isolate that function just like I would isolate a variable. Okay? So in this case, I'm going to add 9 to both sides. X squared equals 16. Then I want to undo the function, which often means applying the inverse function if such exists. In the case of squares for positive x, it's taking the square root of both sides. So what does that mean? Remember, our square root of x squared, as we just discussed, it's not just x, it's absolute value of x. And that equals the square root of 16, which is always positive 4. Well, again, my answer is not just x equals 4, because absolute values, if you don't know already, we'll learn later, have a positive and negative case solution. So plus and minus 4 solve that equation. Think about it. Minus 4 absolute value equals 4, or minus 4 squared is 16, and the square root of 16 is 4, which equals 4. The minus 4 solution for x works as well. So you have to keep that in mind. Sometimes we throw that out in geometry and other problems where you can't have a negative length and it really isn't meaningful to the problem. But you should know the mathematics of it. So again, simple squares and square roots, I want to isolate that square root first and then undo the function, ideally with an inverse operation. Okay? This is how we solve some basic equations. If you know this and you're comfortable with this and these functions or these complications, you're pretty much in shape to get into the more complicated SAT math we're going to develop. So this is a very quick background of our fundamental skills, things you need to pull together to use over and over again on all the different topics for the SAT. I hope it helped. I'm sure we've missed something along the line, but it should be a good background to get you familiar and remember some of the things you might have forgotten.